The buoyant force. What does the buoyant force mean? Well, first, have you ever dropped your swimming goggles in the deepest part of the pool and you try to swim down to get him? Okay, so you feel so frustrating because the water tries to push you back. So, the name of this upward force exerted on objects submerged in fluids is the buoyant force. So, why do fluids exert an upward buoyant force on submerged objects? It has to do with the difference in pressure between the bottom of the submerged object and the top. So, as we can see the image, the buoyancy force is equal to the weight of the fluid displaced. So the formula will be Fb is equal to the density of the fluid multiplied by the gravity multiplied by the volume displaced. So the weight of the object is, as we know, is the mass multiplied by the gravity.
Our objectives for this project were to analyze the buoyant force in a stationary system, to find an equation that describes the forces in the experiment, and to find the length of a string lifted by a balloon mathematically. We are going to gather all the data we obtained from our balloon. The mass of the envelope is equal to 2 grams and the balloon radius is 11.14 centimeters. The total length of the string is 1.47 meters and its mass is 9 grams. It's important to take into consideration the densities involved in the experiment, as helium and air at 20 degrees, and the formula to get the volume of a sphere. First, we will analyze the forces involved and obtain a condition for the balloon's flotation that would help us calculate what we need. As the balloon remains stationary while it lifts a portion of the string, we identify this portion as h. We actually got an experimental value for h, but we will discuss about it later. The buoyant force goes upwards, and in the opposite direction, we have a force generated by the balloon's envelope, another one generated by the helium in the balloon, and a force created by the h portion of string. From this, we can obtain a buoyant force expression, which describes all the forces in the experimental model. To examine our expression, we have to remember that the buoyant force is equal to the multiplication of fluid density, gravity, and the volume of the part of the object that is found inside the fluid. The rest of the forces are interpreted as mass multiplied by gravity. As our fluid in this case is the air and the entire volume is found in it, the volume in the buoyant force formula is equal to the total volume of the object. With this said, our buoyant force expression can be substituted this way, and the gravity can be cancelled. Considering all the data we obtained from the experiment, the only missing value is the mass of the helium. Remembering that the density is equal to mass over volume, and we're talking about the helium in the balloon, its density is equal to mass over the total volume of the balloon. As we have these two values, we can use them to obtain the mass, and substitute it in the buoyant force expression. As our purpose is to know the value of h, doing a bit of simplification, our equation now can be substituted by the corresponding values. With this, we have the mass of the h portion of string. The formula to obtain density will be helpful again, as we have data from the ribbon used in the experiment. Its linear density is equal to mass over length. This helps us find out a relationship between the total length and mass of the string and the mass and length of the h portion, consequently creating this equation. The last step is to substitute the variables. With these procedures, the value for h that we calculated is equal to 63.896 centimeters. We compare this to the measured value in the experimental model, which is 57 centimeters, giving us a difference of 6.89 centimeters and an error of 12.08%. The recommendations that we have for this project are to use a balloon that is as spherical as possible to achieve more accurate calculations, and avoid air currents or spaces that could affect the balloon's stationary position. In this project, we took back some previous knowledge about buoyant force, learned more, and put it into practice to analyze a system in which the fluid is the air. We could derive a force equation from an experimental model and obtain a value through variables and data measured from the experiment. The calculated length of string lifted by the balloon has a small percentage of error in comparison with the experimental value, which proves that we achieve our objective with right calculations.